Have you ever just stopped and wondered, how does an AI actually learn? How does it go from making these completely wild guesses to doing things with like pinpoint accuracy? Well, today we're going to pull back the curtain on the single most important algorithm that makes it all possible. We're going to dive right into the learning engine of AI. So it all boils down to this one simple but really fundamental question. When a neural network, which is just a fancy term for a computer system modeled on our own brains, gets something wrong, let's say it looks at a picture of a cat and calls it a dog, how does it figure out what went wrong and, more importantly, how to fix it for next time? The answer is kind of weird, but also totally elegant. The AI doesn't just scrap everything and start over. Nope, it works backward, starting directly from its own mistake. Right, so this whole process of working backward actually has a name. It's called backward propagation, but pretty much everyone in the field just calls it backprop. And you can think of it as the AI's secret strategy for getting better. Okay, the best way to think about this is like a detective story. Seriously. The AI makes a bad guess, boom, that's our crime scene. And backpropagation, that's the detective. It shows up and starts working backward from that mistake, tracing the evidence of the error through every single layer of the network. It's on the hunt for clues to figure out exactly what's responsible for this mess. So our detective is on the case. It's tracing the error back. But what clues is it actually looking for? What does it need to find to solve the case and make things right? It's hunting for something called gradients. Now, you can forget all of the scary calculus for a minute. Just think of gradients as the perfect recipe for improvement. They're a super precise set of instructions that tell every single little part of the network exactly how much it needs to change to get a little bit closer to the right answer the next time it tries. So how does this all actually work in practice? Let's walk through it step by step. I like to think of it as a blame game, where the error gets passed backward, from one layer to the next. By the end, every part of the network knows its exact share of the blame and what to do about it. We'll even peek at the code that makes it all happen. Okay, step one. The whole thing kicks off right where the mistake happened. At the very end, the output layer. This is where the AI's final guess gets compared to the actual right answer, and we get our first look at the error. All right, let's look at the code. Don't worry, it's not as scary as it looks. So this first bit, DZ3, that's the starting gun. It's just figuring out the difference between the AI's guess, which is A3, and the right answer, Y. Simple as that. That number, that's the raw error. And from that one number, the code then figures out DW3 and DB3. These are basically the specific instructions, the gradients, for tweaking the connections and those little internal confidence styles, the biases, in this very last layer. Okay, so the final layer knows how to fix itself. Now, it needs to pass the blame backward to the layer that came right before it, layer 2. It basically says, hey, here's how much you messed me up. See that variable day 2? That is the error signal being handed back from layer 3. Now layer 2 takes that signal and uses it to calculate its own share of the responsibility for that final bad guess. And, just like before, it then spits out its own set of adjustments to correct its behavior. You can probably see the pattern now, right? The process just repeats. The error, which has now been updated by layer 2, gets passed back one more step to the very first hidden layer. We're getting closer and closer to the source. And here we go again, same deal. The day 1 variable catches the error coming from the layer in front of it. The network then calculates this layer's contribution to the mess. And finally, it figures out the precise instructions for how layer 1 needs to change. The blame has been traced all the way back to the beginning of the network. So, after all that backward passing and blame gaming, what do we actually have? Well, we've successfully created a complete set of instructions, a master plan, really, for the entire network to get smarter. This table here shows you the final prize. At the end of the whole backpropagation process, all those little adjustments we calculated for every connection, every bias, they all get bundled up into one neat little package called gradients. This isn't just a list, you guys. This is a comprehensive toolkit with every single tweak the network needs to make to do a better job next time. Okay, let's zoom out from the code for a second. It might seem like just a clever bit of math, but this is the fundamental reason modern AI is so incredibly powerful. See, Backprop is just ridiculously efficient. Instead of guessing randomly how to fix itself, which would take like forever, it uses calculus to find the fastest, most direct path to getting better. It's like a surgical strike on its own errors. So every time an AI recognizes your face in a photo or translates a language on the fly, or when you see those incredible AI art generators create something from nothing, you're watching the result of this exact process. It's backpropagation running millions, maybe billions of times, turning every single mistake into a lesson. This is the engine that's driving it all. So if there is just one thing you take away from all this, let it be this. Backpropagation isn't just one way for AI to learn. It is the foundational engine that makes pretty much all modern AI possible. It's the simple, elegant idea of working backward from a mistake that unlocks all these unbelievable capabilities. And that kind of leaves us with a pretty wild thought, doesn't it? This is a systematic, purely mathematical process that lets a machine identify its own flaws and then correct them with precision, over and over, on a massive scale. When a system can learn and improve itself like that, you have to ask, how close is that to what we call thinking?